Right. Thank you very much indeed for inviting me. It's a great pleasure to be back in Melbourne on this beautiful day. So my talk today is, can large language models reason about spatial information? And maybe you already know the answer, so you can leave and now, but let's see. Okay, we'll do it that way. Okay, always good to start with a picture. This is from ChatGPT for thinking mode yesterday. Can you draw me a map of the sea route from Melbourne, Australia to Auckland, New Zealand? Where do we start? I mean, how many errors can you find? I mean, Wilson's probability is that we've got some interesting longs on the axis here. We've got non-even spacing on the longitudes. We've got, it doesn't even start at Melbourne. Auckland's in the wrong place. Haruki Gulf is twice. The sea route seems to go through right across the Alps in the South Island. You know, I mean, there's just so many things we don't really know where to go. There's probably some other things I should be labeling in red there as well. I've done multiple things like this. It's never able to draw a map. I mean, things are always mislabeled. I mean, it's so not exactly reasoning, but certainly clearly a lack of understanding about spatial information. I'm walking north with only a compass to guide me. I look down at the compass to check my direction. Well, apart from the fact there's clearly things funny with the compass, if you look at the intercardinal directions, but clearly I'm not walking north. I'm walking in a different direction. Listen, what am I going to get if I say, give me a picture of a wall clock showing the time is 3:20? Any guess? Am I going to get one that shows anything like that time? No, right, yeah. You can see where we're going. We get, you either get 10 to 2 or you get 10:10. You can ask, you can try this again, give it with 10 clock faces. Well, we've actually got 12, but let's not, who's counting? 10 is not nicely divisible into 2 rows unless you had a row of 5 and a row of 2. All showing pretty much the same. I mean, they're not quite the same time, as the second hands are a slightly different place. So basically all the same time. Showing that all 7:30. Again, you know, it's really fixated on this. Why? Well, you know, all the result of training data, I suspect. If you look on the internet, almost, this is kind of a nice, pleasing angle. If you're trying to sell a clock, this is the kind of nice, pleasing angle, it seems. I mean, there's a few examples which aren't like that. Like this one is 10:09, and there's one down the bottom row at 3:07. But you know, overwhelmingly, 10:02, or 10. Sorry, 10:10 or 10 to 2. Ask ChatGPT 03 to draw me pictures of 10 pictures of people shaking their hands. Again, we've got the wrong number of pictures, all shaking hands with their right hands, not their left hands. There's also, apart from the fact that we've got the wrong number, look at the bottom left picture and the bottom row there. Interesting change of color, skin color between the hand and the face. Nice and diverse, you know, full marks for diversity, but the ChatGPT 5 also similar problems. Again, trying to just test out leftness. Is it sort of biased for left? Show me a picture of road New Zealand with cars on it driving in both directions. Well, they are driving on the left, but there's some strange road signs here. There's this one here, the one that says keep left, which isn't even a proper road sign. It seems to be a little label inserted into the middle of the picture. There's this really dodgy kind of 10km/h speed limit there. And I'm not sure, I've been to New Zealand, and you definitely, if you see the Alps, you must be on South Island, and you're definitely not 5 kilometers from, 45 kilometers from Wellington. Drawing a picture of a car, 10 pictures of a car overtaking a bus, the wrong number of pictures as usual. Only one where a car is actually overtaking a bus is everybody's driving on the right. So what about interpreting maps? Here's a little sketch map I drew, and this is GPT-5, and it's doing, it actually, finally, here's a language model, I've tried quite a few, where it actually understands the map. this is actually, I'm not going to go through all of this, but this is a really good summary, textual summary of the map. Okay, earlier ones misunderstood it in various ways. It kind of got it maybe sort of 50-60% right. And then say, how would you get from the restaurant to the charity shop? The restaurant is in the middle of the yellow road and the charity shop is bottom right. And this gives a good description of how to get there. Walk east along the yellow road, to the green diagonal, go down there, turn on the red road, and that's all fine. Of course, there's sort of multiple ways to get there. So then I say, are there any other ways to get there? Yep, there's 2 other ways to get there. But here we start to run into problems. First option, from the restaurant, go west along the yellow road. Okay, that's a good start. Towards the newsagent. When you reach the red diagonal, turn right. Oh dear, we should be turning left. But it does have the right direction, southeast towards the charity shop. Alternatively, the restaurant goes south down the green diagonal. Well, it's kind of omitting the fact we first of all need to go east along the yellow road. But even if we ignore that, then it says to the purple road, and then it says walk east along the purple road. But that's clearly wrong because what are we doing? Sorry, this goes down the green diagonal. When we hit the purple road, we should be going west until we hit the red road. So both of those are wrong. So LLMs are clearly a very active research area. New large language models around all the time. Wait a couple of weeks, you've got another one or an update. And many claims made about them that they can do reasoning. We've got these multimodal models. So I've been involved in a project at the Alan Turing Institute in collaboration with Nigel Shadbolt and Mike Wooldridge on evaluating capabilities and limitations of foundation models, including large language models. So this kind of talk basically comes out of that project. Mike Wooldridge was doing theory of mind. Nigel Shadbolt alignment to human values, and I was looking at a common sense. And in particular, spatial reasoning. I've been working in spatial reasoning since, I met Matt in late 90s, I guess we first met, but I've in fact started my work in spatial reasoning in the late 80s. So I've been almost all my work, or much of my work since then, has been on spatial reasoning. So I'm kind of interested in that, and can large language really understand space, which is kind of, in a way, you'd be surprised if they really could, because clearly they're not embedded. They've learned all of their knowledge from, basically from text and perhaps images. So they haven't grown up in the world. And maybe that's some of the problems they've got about left and right, because they've never had this first person experience of walking around the world, thinking about what's on their left and what's on their right. I've just mentioned I've got a few other LLM-based projects, another couple of projects at the Alan Turing Institute, one on using large language models to analyze argumentations based in argumentation theory. We're looking at BBC question time, discussions and classifying degree of left and rightness of statements, and whether arguments are really supported or not. Another one where we're looking at neurosymbolic reasoning. I'll mention that very briefly, I hope, at the end of the talk. A new project on geo-LLMs, and an ESRC NSF project, which is where I'm going to project workshop next week in Washington, DC, where we're looking at extracting spatial relationships using LLMs from a couple of historical corpora, one Holocaust survivor testimonies, and the second one Lake District travel writing from the 1600s to the 1800s. So people like Wordsworth and Coleridge. I just this is an archive paper from a couple of years ago, just showing, or maybe last year, just showing the impact that LLMs seem to have had on our scientists' lives. This is 4 words, pivotal, integrate, showcasing, realm, kind of bubbling along at roughly the same frequency per million words of scientific paper. And then suddenly 2210, frequency of all these words seems to shoot through the roof. And what happened in 2210, of course, ChatGPT got launched. Do we use large language models to write our papers? Of course not. Do we use them to review our papers, to write applications? No comment. So what kind of spatial reasoning to test? I've been interested particularly in qualitative spatial reasoning, which is ubiquitous in natural language. We talk that we're in the room, the computer is on the desk, the water's in the bottle, the microphone is in my ear, or maybe it's on my ear. So there's, the way we talk about the spatial world and indeed the temporal world as well. Before now, I had breakfast and And yesterday I arrived, the day before the current day, I flew on to Australia from China, and so forth. So I can't cover all of that. I'm going to be talking a little bit about merit topology, which is about parenthood and connection, directions, a little bit about route descriptions, perhaps temporal. I'd like to cover spatial temporal as well, but I'm just going to be looking at temporal reasoning today, and cardinal directions. There's a big question of how do you actually evaluate large language models? And of course, everybody's favorite way of doing this is to use benchmarks. You write a benchmark, and a set of questions, you make it easy to evaluate. So it's typically multiple choice. And then you get hopefully the large language model to choose one of the multiple choice answers, and then you just evaluate it. Of course, that makes it easy to evaluate, but it makes it it's not clear whether you're really testing what you want to test. Are you really measuring? Is that benchmark really a good test of the underlying capability you want to measure? Is it has there been leakage from the benchmark into the training set of the LLM? You can get artifacts in the data set in the benchmark. So I mean, there was a well-known way of trying to evaluate common sense in AI systems, the so-called Winograd schema challenge, of which you see one example here. The trophy wouldn't fit in the case because it was too big, because it was too small. If it was too big, then presumably that it refers to the trophy, and if it was too small, then presumably it refers to the case. And the idea is you can only answer this if you understand common sense and notions about space. And that's maybe a reasonable test. This one is less good because you can look up statistics of, sports cars tend to go fast, buses tend to go slow, and therefore just based on the statistics without really understanding anything about it, you can just then make an educated guess that if something's going fast, it must be the sports car, and if something's going slow, it must be the bus. And so, one way of trying to get around this, some of these problems is then to try to use automatically generated or synthetic benchmarks. That kind of helps get around this leakage problem because you can generate new tests all the time. We had a paper in Itakai 24 where we had this sort of steps of simulated worlds, and you could generate, thousands and thousands, millions of test examples if you want to. You've got to be careful not to rely on a perceived connection between tasks and methods, and assuming that just because humans solve a task in a particular way, that a lot AI systems don't do it the same way. And that was kind of the ultimate downfall of the Winograd schema challenge as a test, that actually you were able to solve it using sort of other non-human-like ways. And there's a nice paper in the AI journal last year which kind of delves into that, not by me, but some other guys, including one of the originators of the test, Ernie Davis. You really want to get sort of tests that span as much as possible all incident, target, problem domain in some kind of reasonably fair way, so there's an appropriate balance between the different kinds of things you want to test. There's this real tension between tests that are easy to evaluate and tests that are definitive. It's a bit like looking for your keys underneath a lamp. It's easy to do, but it's not necessarily where you're going to find enlightenment or to find the thing you're looking for. And if you do this kind of test, you really want to be careful just about saying we've got an accuracy of 0.95, but maybe the other 0.5 is, particularly, it's not the thing that got wrong is not spread evenly across all kinds of instances, but concentrated on particular kind of examples. And you'll see some examples of that later on in the talk. I did do a little bit of work a couple of years ago on something I call dialectical evaluation, which is kind of really nice ideas. It's a bit like having a PhD viva with the system. You basically have an extended conversation and you can really probe it. Of course, the trouble is this is not automatable, at least it's not obvious how to do it. You kind of have this extended conversation. I have some examples in this archive paper. But it's really expensive. You really need another human. Maybe you could use LLM as judge, but then you're relying on the second LLM to do a good job. The nice thing about this is you can test notions such as what John McCarthy called elaboration tolerance, which is the idea if a system can solve one problem, it should be able to solve a small variation of that problem without completely rewriting the system. So a system is elaboration tolerant if basically it can answer this question and a whole bunch of similar problems without any changes or minimal changes. And of course, you can really test explanations, which may or may not, in the case of LLMs, actually align with the answer. So here's my first actual benchmark one. This is one we invented to test cardinal directions. We first appeared in COSIT 24 last year, and then because there were so many new language models had appeared since then, we sort of ran a whole bunch more tests in that was appeared in the qualitative reasoning workshop at ICHCAI this year. And so basically, this is instance of generating lots of questions from a small number of templates here. So here we've got 6 templates. The things in color, the things which can get changed in the instance of the template. So we can change the person, you are, I am, we are, he is, she is. You can change the mode of transportation, of locomotion, walking, hiking, running, pogo sticking, etc. You can change you can go south along the east shore, north along the west shore, and all other combinations, including the intercardinal directions like northeast and so forth. So that gives us 10 times 6 times 8 times 2, which gives us 5,760 questions altogether. And then we test a whole bunch of large language models. So the orange bars, no, the lemon bars are for the original COSIT paper last September. The orange bars are the ones which are in the QR25 paper this year, and the blue ones are for large language models which came out since then. Yeah, so it's showing you the kind of, and you can see if you look at the lemon bars, then actually the best one was this one up here, one on the middle of the third down on the second column, which was ChatGPT 5 Turbo, which is by no means the most recent model at the time. We're really quite surprised that the best model was not the most recent, or indeed the largest model. Now, the best model, when we did this valuation within the last month, is now GPT-5. Which is it's sort of actually basically the same performance as the OpenAI's O1 model. The models here which have got black sort of surrounds to them are reasoning models, as opposed to just vanilla models. You can see that the top 1, 2, 3, 4, 5 models are all reasoning models. So there is clearly seems to be a tendency for these models to be the best. The red vertical line is the guess rate. So you can see they're all doing better than the guess rate. Oloma 2, not only just better, but at least it's just slightly above the guess rate. Most of them are quite a lot better than the guess rate. So they are showing, quite a reasonable performance here. What else was I want to say about this? The top models are all basically all commercial models. The best open source model, I think, is this one here, the OSS model from OpenAI. There's also DeepSeek from Reasoner, which is the fourth one down. Yes. So the commercial closed models and the reasoning models tend to be doing best here. This is kind of interesting. So let me just go back to those templates. The 5 of these templates involve aerial objects. So things which have got a basic area. So we've got lakes, we've got parks, and we've got an island. And actually, there's an interesting thing about the lake versus the island. So if you're on the east shore of a lake, and then the lake is to your east, but if you're on the east shore of a lake, then the lake to your west. But you're east shore of an island, the lake is to your east. But they generally seem to cope reasonably well with understanding that. This 4th template involves a linear object, a road. Okay, so you're walking east along the south side of a road, which runs east to west. For some reason, this seems to be much, much harder than the ones that involve aerial objects. So here you can see the performance of the top 10 models with on the left, it includes template 4. On the right, we exclude the template 4 results. And now you can see that 1, 2, 3, 4, well, basically, down to here, we're getting a 9.99 or 1 of accuracy. So this one is really creating, template 4 is really creating problems. And so much so that GPT-5 has gone down from basically the list number of instances 960 out of 960. We only did a single repeat of GPT-5 for cost reasons. So we're getting, it's roughly 50% of accuracy on that, was basically, well, it's 100% on all the others. GPT-OSS gets 0% on template 4. You'd think that statistically it would just get some, even if it's kind of guessing, it would get some of them right, but it doesn't get any right. It's doing quite well. You've got 8 possible answers of 8 possible cardinal and intercardinal directions. It gets none of them right. Kind of weird. Looking at how do these, of course, the mode of locomotion and the person form shouldn't make any difference to the answer. The only thing this depends on is where I am, and that when I'm going north or south is irrelevant as well. That was just thrown into to confuse things slightly. It would make a difference if we were also asking about left and right, which is another experiment I won't talk about today. So here you can see that the best model is GPT-5. It doesn't make much difference. Unicycling, as you might expect, is actually slightly the worst, but really not by much. Some of the weaker models like Claude 3.5 Sonnet on the left, unicycling, perhaps not surprisingly, is worse than hiking. But even though within that, you'd expect that walking would be right up there if you're just thinking about number of web pages or whatever documents with walking in. Walking actually occurs more frequently in typical corpus than hiking, but hiking still seems to be better. This is mean locomotion score for other selected models. And again, you can see some of these are really getting a much worse performance. Interestingly, was it this one? Oh, yeah, so here, perambulating really does pretty well, which is kind of it's a little surprising, really. Person form, GPT-5, it does make some difference. Notice here the first person and the second person, I am, you are, we are doing better than the third person, she is, they are, he is. And she is, perhaps he is within the error bounds, but maybe slightly worse than he is. But that's not is not the same for all the other models. So, for example, we get it the same for Claude 3.5 Sonnet. First person, second person are better than third person. But for here, GPT-OSS, same as GPT-5, they are basically the third person forms are better than the first and second person forms. I'm not going to go through all of these models here, but you get the idea. By correct answer direction, you can see that all models here on this slide, all models except for Llama 3.7b and Claude 3.5 have better cardinal directions than intercardinals. So we sort of see that. So you can see here we've got north, west, east, south. This is by the correct answer. It gets the correct answer much more frequently than the intercardinals. Azure 01, not so much difference, but again, the cardinals better than the intercardinals. Ditto for Azure for 4.0. For Llama 3.7b, North is much worse, surprisingly. And again, that's also true for 3.5 Sonnet. It seems to have more problems with North than, say, Southwest and Northeast. We looked at tokens as a proxy for reasoning effort, and here you see that this is which model is this is GPT-5, and you look at the reported number of tokens, you can see that it's using more tokens to get the compute answer when the answer is intercardinal direction compared to a cardinal direction, and that kind of makes sense, at least in languages where the intercardinal direction names are composed of 2 words. There are a few languages in the world where the intercardinal directions are not composed of the 2 surrounding cardinal directions. Kind of some weird, sort of unusual languages, but most languages in the world are like this. And so that's I think that's interesting that it looks like somehow the computation for the intercardinals does involve reasoning about both the cardinals as well. You can also look at the tokens if it gets the answer wrong, it spends, in general, this is for a 001, there's a 01 running on the Azure platform. You can see spends more time, but still gets the answer wrong. Whilst if it gets the answer right, it tends to spend less time. This is an effort for correct and incorrect for each of the directions. And again, you can see that so blue is correct, yellow is incorrect, and you can see in general the blue is lower than the yellow. So we're basically, if it's getting it correct, it's doing it in less time than when it gets it. It spends more effort but still gets it wrong. And this is completion tokens by correct answer on a 1. And again, you're seeing a similar pattern there. I just want to skip over this to make sure I get through the slides. And this is by template usage. And so you can see the 5 of the template have very similar kind of patterns broadly. But template 4, it's found it much harder. The mean number of tokens used to answer T4 questions was rather higher, and they're doing much worse as well. Distribution of GPT-5 incorrect answers by what the correct answer should have been. So this is for the times when it got it wrong, and so when it's getting it wrong mostly for the intercardinals, north, east, west, southeast, northeast. Again, north slightly out of place there perhaps. So east and west are when it's at the times when it's least likely to get it wrong. This is just slightly interesting. There's a confusion matrices for some of the older models, and what you sort of see is you'd expect obviously you really want everything to be on the leading diagonal, and you can see for the cardinal directions it's fairly well concentrated on leading diagonal. For the intercardinals, these models are not doing so well, and you do seem to see this pop out sort of square coming on this one and this one in particular. And what that's showing you actually is it's not confusing it with the neighboring intercardinal, it's confusing it with the opposite intercardinal. So it will confuse northeast with southwest and northwest with southeast. Just here's a typical short incorrect answer from GPT's OpenAI's open source model, OSS 120B. He's running east along the south shore of a lake and then turns around to head in the back direction. It came from which lake. And so, here's the place where it starts to goes wrong. And then he says it gets it right, it's still to the south. But it's got the wrong answer. It can reason correctly that if you turn around, it doesn't make any difference. But unfortunately, it's already got the wrong answer. On some of the models, not all of them, most of the recent models you can't, the reasoning models you can't control temperature. For the ones where you can, we did this one experiment. This is with, I think, C5 Turbo, yes. And you can see we did, where we could, we set the temperature to 0. You can't always do that. So this is showing you the effect of, as you increase the temperature, basically your accuracy drops. Which perhaps, you might expect that if you set the temperature high, it means you've got a greater probability of not choosing the highest probability answer. And so that, if you assume it's reasoning correctly, then the highest probability answer should be the correct one. So by not always choosing the highest probability answer, you'd expect that maybe the accuracy would drop. So that's an expected result. This covers them using quirks. I only saw this in the C5 Turbo model, temperature 1.2. We got this sort of strange new direction invented, which is a mixture of Roman alphabet and Chinese alphabet, and invented this new direction called southwest. So we only saw that in the C5 Turbo model. And we're running Olama DSeq R1, a distilled version of R1. We actually had it going on for about 3 hours, and we just had to kill it in the end. It just kept on going round and round, and the same sentence kept on repeating. But if we use the default temperature rather than temperature 0, they very quickly returned and gave us the right answer. And this is just part of this sort of the reasoning chain from that particular model. And R1 is just kind of this very informal kind of chatty mode in its sort of reasoning. It's a really kind of strange form of reasoning. Okay, let's break this down. Then so this kind of seems reasonable, and then it says things like, let me visualize this, and then it says, since the pond is north of A and A is somewhere between B and C, but closer to one or the other, or is it the other way round? It's a reasoning chain, but it's kind of pretty unsure of itself as it goes along. And this is just one small portion of this 3-hour long transcript we got out of it. Okay, so some of this little bit of whoa. I've spent more time than I expected. So cardinal directions benchmark summary, best model is now a lot better than it was, saturated by the latest models. Our models don't generalize in the way we expect. And some of these things are really expensive to run. I'll come back to that again in a moment. I'm going to quickly cover this more recent work we've been doing on testing a large set of qualitative spatial and temporal algebra. I'm going to very quickly to give you pictures of these algebra on the next couple of slides. But basically, we've got 3 temporal algebra: the interval algebra, the point algebra, and the in this last one, the so-called Indu calculus. This is the number of relations in each of these calculus. Each of these calculus consists of n jointly exhaustive and pairwise disjoint relations. And we're going to ask 3 kinds of reasoning question. What's the inverse relationship? What's the name of the inverse relationship? What's the composition? So if you know that the relationship between A and B and the relationship between B and C, what's the relationship between A and C? And finally, the conceptual neighborhood. I'll illustrate that on the next slide. So here's one of those calculus, the so-called RCC8 calculus. This is region connection calculus with 8 relationships. And so you see these 8 relationships, jointly exhaustive, pairwise disjoint. And by conceptual neighborhood, this is just externally connected, and the conceptual neighbors are the relations which it might move to next, which could be disconnected or partially overlap. If these regions are moving continuously or deforming continuously, those are the next possible relationships. So the test for the language model then is what are the conceptual neighbors of EQ, and you expect to get these relationships here, these 5 relations. Okay, and you can simplify that calculus to get RCC5, where you collapse some of these relationships. You can also make it more complex by breaking. Oh, seems to have got a problem there with my overlays, but basically for the disconnected and externally connected, if you've seen the regions can be not necessarily convex, but then you can have notions like this where the white region is partially inside the grey region is partially inside the white region, and you get a total of 22 regions, 22 relations if you do that. 3 qualitative temporal calculi, point algebra where 2 points can either be before, after, or equal. Interval algebra, which is illustrated by these things. The one region interval can be before another, they can be equal, they can overlap, and so forth. And so there you get these 13 relationships. On the Indu calculus, then for the ones where they're not part of the other one, like before, you can be before and bigger, or before and shorter than the other one, and before and the same length. And finally, a couple of direction calculi, the so-called star calculus, where you have these 8 open segments, and also whether they're at exactly the same point, and this cardinal direction calculus, where these 4 quadrants, and also the cardinal directions on top. If you just look at the performance of across those different calculi, which are the columns, and these are all the models we ran, GPT-5, Gemini 2.5 Pro, you can see, and so the yellow means doing well, blue means doing badly. You can see that even GPT-5 for RCC22 is doing pretty badly. Its best result is all models do badly on RCC22. Even GPT-5, it's still only getting 0.72 on that. Point algebra with only those 3 relations. Most of the models, except for the really small ones here and the older ones, are doing pretty well. In Indu, which has got 25 relationships, which is actually more than RC22, but so it's not just the number of relations which is causing the problems. It's just, it seems to be generally harder calculus. It's into slightly more, 25 versus 13 relations. It's fairly similar performance. Interestingly, we've got two different versions of this Merry topological calculus with 8 relations. We've got the RCC8 one, which I showed you just earlier. We've also got another one from Max Egenhoff and his colleagues at Maine University in the US. And if you look at the picture of the relations, they're the same, but they've defined in a different way. They find that the language models find it much harder to reason about the 9 intersection version of that same set of relationships, but when they're defined in a different way. And you can see that here. This is comparison of GPT-5 and RCC8 in the 9 intersection. We ran it 3 times. If you see a 3 here, it means it got it correct answer in all 3 instances. But you can see that RCC8 they're performing differently on these 2 calculi, and in generally worse on a 9 intersection. We anonymized. We ran the examples in several different ways. We used infix and prefix notations. We used it with the correct relationships. We also anonymized, as of saying, externally connected. We would just invent a new word. So it was had to try to reason from first principles. We also had it with a schematic schema representation. So that's like here, we're kind of explaining relationships using this kind of a notation, using sort of letters. And illustrating the relationship spatially like that. And you can see that those 2 ones with the schematic, it does indicate a worse performance. Some of the earlier models, they do have a difference between anonymous and non-anonymous, but the latest models, they don't seem to have much of a difference there. I'm aware of time here. I'm going to skip that. There was some work done by Marcus Ragni, comparing, he asked humans, okay, in general with the composition table, there can be multiple possible answers for, and he asked in this work, he asked German speakers and Mongolian speakers to pick their preferred, their most likely, their preferred single answer from the composition of, say, X is to the left of Y and Y is to the left of Z, and what's the relationship between X and Z, or whatever the relations were. Then and the Germans and the Mongolians, even though the language is very different, tended to choose the same relationship. Do language models do the same? And the answer is no. So basically, you can see at the top here, this is get this the right way around. So yes, so this is the human. So basically, you can see here the Germans and the Mongolians are pretty much agreeing with each other. About 0.84, and the 3 repeats agreeing with each other, but over here and here the large language model is not agreeing with either the Germans or the Mongolians, and similarly the other way around. This is just showing you that actually the results on this data set, this benchmark, agreeing fairly much with the general evaluation in the AI index on this website of how the model is doing. This seems to be a little bit more challenging a data set than the ones they use there. Cost trade-off, this, are you comparing cost per 1 million output tokens on a log scale versus accuracy. You can see that, the open AI 01 is very expensive, but by quite a long way, but by no means the best. Whilst some of these things are very expensive, but also very bad. Costs 1 repeat. 01 is really expensive. GPT-5 next most expensive, but also generally the best. Okay, and so summary from that. Domains of the 2 direction calculus similar, but and the RCC8 and 9 intersection, but we get different sets of results, which suggests these large language models can't really generalize across representations. We sometimes got hallucinated relationship names. The calculus with the largest number of basis relations were most prone to not following the question rubric or hallucinating. So when it was particularly harder, there's we might want to be able to run small models on our laptops, but actually those models really struggle with these kinds of benchmarks, at least at the moment. They don't seem to show the same preferences as humans, and whilst most of the reasoning chains generated by the large language models, they seem to be unlike human reasoning. And maybe this all comes out of the fact that the large language models aren't grounded. And they, surprisingly, they really misunderstood, couldn't understand equality. So you'd expect that, if A equals to B and B is in some relation R1 to C, you'd expect to be able to infer easily that A is in that relationship to C, but they're not very good at that. Okay, I'm aware I should be stopping. I'm going to skip that. Just very briefly mention this work on combining doing neurosymbolic work where we use a large language model to translate into a symbolic representation and then use a logical reasoner. And so this is a benchmark called Step Gain. We published that in AAAI 24. We only gave the large language model the stuff on the left. This is just for your benefit to show you kind of what the setup was. And in this AAAI 24 paper, the results in blue are when we use a large language model to translate into symbolic form. And then with the best of those, we're getting basically 99 or 100% accuracy compared to these language models here, where we're just using them either as they come or with chain of thought or tree of thought and chain of thought. And we sometimes get some decent results here, but still not at the level of users in symbolic reasoner. There were some bugs in that space, in that benchmark, and we've extended it now to something called decompSR. There's a archive paper just out. We've also got versions of that with Swedish and Hindu, and we've also extended it up to 100 steps. And you can see here that on the left here, we've got k equals 1, k equals 2, and k equals 50 for the different models. And you can see that as k gets big, the accuracy is really dropping down here. The red dotted line is the guess rate, so we start doing worse than the guess rate. This is R1, this is GPT-5. So this actually holds up pretty well. Even at k equals 50, we're still at 0.81 accuracy, only dropping to 0.27 by the time we get to 100. So it still drops off. This is English versus where anonymize. If you anonymize the relation names, we do really badly. And I think there's just effective shuffling and noise. We looked at that. Just point to this software which was used to run these large language models experiments is open source. You could just download it from this GitHub repository, and it does well with failures and backing up and replaying, and it runs across a wide set of APIs. Okay, I'm going to stop there and ask for questions. Can this, all the stuff being inquired without embodiment in general? Do we need symbolic reasoning in general? I think so. And thanks so much, and to my collaborators.